So this is number 12 on chapter 9. It reads, a force platform is a tool used to analyze the performance of athletes by measuring the vertical force that the athlete exerts on the ground as a function of time. Starting from rest, a 65-kilogram athlete jumps down onto the platform from a height of 0.6 meters. While she is in contact with the platform during the time interval 0 to 0.8 seconds, the force she exerts on it is described by the given function below, as you can see right here. And part A asks you, what impulse did the athlete receive from the platform? So to find impulse, so I just drew this diagram. This person is jumping onto the force platform, as you can see here. And I also wrote down all the knowns. It says her mass was 65 kilograms. She's jumping from a height of 0.6 meters. Her time is from 0.08, and this is a given time function, given force function that is dependent on the variable time. So remember that impulse is also equal to the integral of the force times the time, the change in time. Or it can also be known as force times delta t, but in the case of which the force is changing and dependent on time, you want to do an integral. So we know the integral and how to set it up because it states that it takes from 0 to 0.8 seconds for her to land on the platform. So this is going to be your lower limit, and this 0.8 will be your upper limit. The force given was this, 9,200 t minus 11,500 t squared dt. And when you set this in, then you would want to take the antiderivative, which is going to be, since it's t, raise it to 2, divide by the new power, 4,600 t squared, minus 11,500 divided by 3 t cubed, based on the same idea as the one before. And then you would want to plug in the times. So you want to plug in 0.8 minus plug in 0, but in this case 0 will just give you 0. So when you plug this in and solve, delta P or J will be equal to 981.33 kilograms times meter per second. This will be the impulse that the person exerts on the platform. And then for part B, it asks you, with what speed did she reach the platform? So with this one, you actually don't need to use momentum or the concepts of momentum. You can use energy principles. So remember, when she's starting out by jumping onto the platform, she starts out with an initial height or a potential of gravity. And then just before she lands on the platform, she's going to have all of that potential of gravity transferred into kinetic energy. So when you set up the mechanical energy equations, you do ME initial equals ME final, and then she initially has potential of gravity, which gets all the way transferred over to kinetic energy. And then when you set up the equation, you get VF equals square root 2GH, and you know the H and you know what G is equal to. And you eventually get V final, which is equal to 3.43 meters per second, which is the speed right as she is about to land on the force platform. And now part C, it's a little more tricky. It asks you, with what speed did she leave the platform? So you can't just do energy because it's assuming that the force is the same, which actually isn't, because when she's just lands on the platform, there's the force of the impact that stops her from going straight down into the platform. So there's going to be the force of the impact that's going to be stopping her. And then there's also the normal force that is counteracting the force of gravity that she exerts on the platform. And then there's also another force, that's the impact of the jump, which is the impact that helps her push off the platform. So the total force, which is F, is going to be F of the normal force plus F of the impact that stops her, and then F of the impact that helps her jump. And then because F, delta P equals F times delta T, and delta T is the same for all of these, it's going to just transfer over to delta P total. Impulse total is equal to the impulse of the normal force on her, impulse of the impact that stops her, and impulse of the impact that helps her jump off the platform. And because you want to find the speed just as she leaves the platform, you want to solve for impact of the jump. And you solve for delta P impact jump. And you know this, the 981.33 for the total, it was found in part A. And then impact of the normal force is also equal to force times gravity times delta t, which is going to be 65 kilograms times 9.8 meters per second squared and 0.8 seconds, which is given in the problem. And then the impact of the stop is going to be what you found, NV, and you found that the speed right just as she's about to land on the platform is 3.43 meters per second, so you just do NV. And when you solve for it, you're going to get delta P of the impact that helps her jump is going to be equal to 248.8. And that is equal to MVF. So you solve for VF, and you're going to eventually get 3.83 meters per second. And if you're wondering why she has a slightly faster speed, it's because she's pushing off with her legs when she lands on the platform and then when she's about to jump. And this gives her that extra speed that's able to have her be able to jump a little faster when she lands off the platform. And then part D, it asks you to what height did she jump upon leaving the platform? And again, this is your energy. And you realize that when she's jumping off the platform, it's all kinetic. And then when she reaches her maximum height, she's going to have just potential because at the top of her maximum height, there is no speed. So all of her kinetic initial and the initial becomes gravitational potential. So when you solve for it, you're going to get HF equals half VF squared over G. You know that 3.83 meters per second was your final velocity as found in part C. And then you know what G is. So you're going to get eventually HF equals 0.748 meters, which makes sense because since she left the platform with a greater speed, that greater speed will equal a greater kinetic energy, and all of this will transfer into greater potential of gravity energy, so it should lead to a greater height, and that is how you solve the problem.